Good afternoon, everyone. I'm Faria Tasnim from Department of Aeronautical Engineering of Military Institute of Science and Technology, Dhaka, Bangladesh. MIST is the pioneer of aviation sector in Bangladesh. I'm going to present our project for RAeS International Light Aircraft Design Competition 2022 to 23, and I'm speaking on behalf of my team, MIST AEROBAT, and the name of our aircraft is Electrolight. Here is my team members along with faculty advisors and mentors and motivators. These are the given design and mission requirements as circulated. For this competition, we have been assigned to design a fully electric two-seated aerobatic aircraft. Two major requirements were having a minimum of 20% battery capacity remaining after the completion of aerobatic maneuvers and the structural G-limit of +6-3. Our overall design parameters are on screen, which includes maximum cruise speed of 250 knots and stall speed of 60 knots. The aircraft has a wingspan of 7 meters and fuselage length of 7 meters. The payload of 200 kg can be replaced by a pilot and a battery of 86 kg weight as mentioned in the mission requirements. Here is the structural configuration and component position shown in the wireframe view. We have chosen tactical configuration for our fuselage. The wings are slightly dihedral and slightly tapered. Conventional tail configuration has been chosen to fulfill the requirements of using mechanical actuation devices. We have chosen tail dragger configuration for landing gear for keeping ground clearance during takeoff due to presence of propeller at the nose section. Here are the selected aerofoil used in our aircraft after comparing previous aerofoil. We have chosen NACA 1412 for the wing due to its high lift and moderate stall characteristics. For the tail, we have chosen NACA 0009 because of its symmetric load distribution and minimum drag characteristics to maintain better stability. For our aircraft, we have selected lithium-ion battery pack due to its high energy density and availability compared to other battery packs. The weight of total battery is 500 kg for an endurance of 30 minutes and energy density of each cell is 250 watt-hour per kg. You can see the placement of battery packs in the fuselage nose section and the wing section. One of the important considerations of this competition is the fulfilling of power requirements for the maneuvers. For completing the maneuvers, high amount of electric power is required. Our electric system distribution has 4 battery packs, 2 in nose section of the fuselage and 1 in each of the 2 wings of the aircraft. Battery has been incorporated in the wing section so that the aircraft does not experience movement at the nose section. We have considered using battery management system to utilize batteries up to their potential to make sure the motor gets enough power. Motor model MRAC 348 has been selected for the propulsion system of our aircraft due to its high RPM range, enough torque, flexible electric power requirements, and flight weight. To deliver enough thrust, a 3-blade fixed-pitch propeller of 1.7 meters in diameter has been used. The Clark Y airfoil, suggested by the planemaker software as an ghost propeller blade airfoil, has been chosen. These are our aircraft aerobatic routines simulated. Although the pilots use these names a lot, their arithmetic codes are utilized to identify these sequences. You can view the flight path executed aerobatic routines in this photo. Now, we are going to show a short flight simulation video. As you can see, the aircraft is taking off and gaining altitude. After gaining over 1,500 feet altitude, we have started the basic loop maneuver, which is RAeS 7.7411. Here we can see the basic loop maneuver. Now the aircraft is doing a half-Cuban maneuver having RST 8561 and 9142. During this flight, the aircraft was slightly unstable due to our low configuration flight controller. Now the aircraft is starting the hammered maneuver, which is indicated with RST 5211 due to the absence of a skilled civilian aerobatic pilot in Bangladesh. The maneuver was not executed correctly. Next, the aircraft is initiating a 180-degree turn, which is denoted with RST 2211. And finally, the aircraft is doing a basic roll indicated with RST 1111 and 9134. Next, we are going to see the aircraft performance of our aircraft. Here is the flight envelope of the aircraft. As you can see, the stall speed is approximately 31 meters per second, which is equivalent to 60 knots. And maximum cruise speed is 129 meters per second or 250 knots. Now, we are going to validate our flight envelope through another flight simulation video. As you can see, the aircraft is stalling at approximately 60 knots speed. Maximum cruise speed is 250 knots and the maximum diving speed is around 400 knots. Here is the outcome of the competition. Our aircraft has the potential to improve overall battery performance significantly in the electric aircraft. The aerodynamics of our design could advance electrical commercial aircraft. The significant design outcomes are lightweight and improved stall characteristics. From the competition, we have learned team collaboration and time management skills. We have learned about the designing of an electric aerobatic aircraft as well as analyzing its performance through extreme simulation. We also had a real-life experience in project management and application of our theoretical knowledge. These are the future development recommendations of our design. Our aircraft provides reliable battery management system only in theory. There is a scope for development using advanced algorithm and models. Our pilot is not professional, which is why the stability of the aircraft was arguable. We can fine-tune the stability to improve the aircraft performance. Finally, though our current design shows acceptable performance, it can be tested through various tail and wing configurations. With this, I am concluding the presentation. We are truly grateful to the board for giving us the opportunity to present our design. Thank you very much.
I'm slightly sweating now.